Hello, in this lesson, I would like to talk about differentiability or not differentiable. So the title is differentiable or not. Okay, how do we decide if a function is differentiable at a point, right? So we have the definition that if a function is differentiable at a point A, then this limit should exist. And if that limit exists, we denote it by the derivative of f at A is that limit. And about this discussion in our previous lessons, okay, so view this, we have proved a theorem. And this theorem says if f is differentiable at A, and then it is continuous at A. So this theorem has proof if f is differentiable at A, then it is continuous at A. Okay, so this theorem established the relationship between differentiability and the continuity at a point. And you can also, for more details and discussions, you can refer to the other recording, okay? But here I am basically summarizing this one more time. So you'll hear about this more than once. Okay, so refer to that recording. So differentiability at A guarantees the continuity at A, right? So this relationship is established. Now, continuity at A, well, the definition of continuous function guarantees that if it's a continuous at A, then the function has a limit at A, right? So limit exists is also guaranteed. So the relationship between these three concepts, differentiability, continuity, and limit, and they are set up in this relationship. In other words, if we have differentiability, then we have continuity. If we have continuity, then we have limit. However, this is a one-way street. This is a one-way street. It's not a two-way street. Because if limit exists does not guarantee continuity, right? We have plenty of such examples. So counterexample includes, for example, we know the limit. Okay, for some of you, this might be just there might be a repeat, right? If x approaches 2, right, and we look at a function which is x squared minus 4 x minus 2. Obviously, this function is not continuous at 2. It is not even defined at 2, but this limit does exist. Okay, so we have learned techniques to find such limit, which is going to be factor the top, right? Factor the top, and because x approaches 2, it's not equals to 2, so x minus 2 is not 0, x minus 2 not 0, so this will be reduced to let me make some more space for it. Okay, so that will make it to be the limit of x plus 2. And then it will become a direct substitution. So the limit is going to be 4. Okay, the limit is 4. But this example tells that, well, limit exists, but it's not continuous, right? So this isn't there. We have plenty of such examples. If you recall all the homework you have done, many of them falls into this category. So limit does not guarantee continuity. And continuity does not guarantee differentiability. Okay, we have a perfect example, which we're talked about this function. Okay, the absolute value function that we all know and know very well. This function is continuous at 0, right? It's continuous at 0, but not continuous at 0, but it's not differentiable, right? Not differentiable at 0, not differentiable at 0. So we have all these examples in our discussion previously. So now here is just we're just summarizing these examples. But as we move forward, right, our topic today is how do we determine if a function is differentiable or not? So how do we draw that conclusion? Okay, so let's see what will make a function not differentiable at A. Okay, there's a logical, very simple logic we like to review, or for some of you maybe review, for some of you maybe you learn it for the first time, right? This is how it goes. There, okay? If A, then B, right? So if this is true, right? If A happens, then B happens. Then from here, we can say if not B, then for sure there's not A. So in this simple logic, we can apply this simple logic to look at these relationships. Okay, we can look at these relationships. So we're going to have the following discussion. We have two examples to go over. And so we're going to develop a strategy. We have the logic here. So we have this basic relationship, right? So we basically have, if we call this capital A, and this is, maybe I can set up a table. Yeah, let me set up a table. So that would be easier to move around. Okay, with 3 columns. 3 rows for now. Okay, differentiable at A, right? Differentiable at A. When I transport these, the software has some conversion behind the scene that takes place, right? Continuity at A. Okay, so continuity at A. So that's it still doesn't work. Okay, continuity. Oops. Continuity at A. Okay, and that will lead to limit at A. Okay, limit, still doesn't do the conversion, a limit at A. Okay, so we have these, we have this established. So how does it apply when we determine whether it's differentiable or not? So we're going to focus on our topics. All right, we're going to focus on our topics. Our topics is under what circumstances we can use these to determine it is differentiable or not differentiable. What we can do here, okay, so we're going to call this 3 columns. Okay, I'm going to insert a row at point 1. Okay, I'm going to insert a row. We don't need this one. We'll call this a statement A, statement B, statement C. Right? So based on the logic we just learned, okay, so knowing this logic actually is very useful. It's very, very useful. So obviously from A, we get to B, right? If A is true, A to B, right? A to B and B to C. And therefore, we can say A to C. If A is true, then C, right? So if it's differentiable, then limit at A exists. If it's differentiable, continuity exists. So from this logic, right? From this logic, we're going to draw the following conclusions. Okay, I'm going to draw the following conclusions. Since if it's differentiable, if f is differentiable at A, then this is the theorem, right? F is continuous at A. This is the theorem we just proved. Hold on, sorry. It's proved, right? So this is the theorem we have proved. Then, so this is the if A, then B, right? So A is that it's differentiable, B is that it is continuous. So what would be true based on this conclusion? That if not A, then, I'm sorry, if not B, then not A. Okay, if not B. What is not B? Not B is, this is B, right? This is B. Not B means it is not continuous. It's not continuous. Then not A. Then not A. What is not A? Not differentiable. We put a not. I hope you guys get this logic. Okay, get this logic. If f is not continuous, then it is not differentiable. So if we know a function is not continuous at A, then it is not differentiable. Okay, the same is with A and C, right? A and C basically says if f is differentiable at A, right, then f has a limit at A, right? Then f, because if it leads to A, if A leads to B, B leads to C, then A leads to C, right? So if f is differentiable at A, then f has limit at A. So this statement is true. This is true. Now, what is if not C, then not A? So if f has a limit, if f has limit, the opposite of has limit is does not have limit at A, then f is not different. Then f is not differentiable at A. I hope you guys get that logic. I hope you get that logic. So this is just a simple. So you instead of learning one theorem, you're learning two. You're learning a pair. Okay. So if we don't have limit, we have no differentiability. If we have no continuity, we have differentiability. But if we have continuity, does that guarantee differentiability? We are in our earlier discussion, we know it doesn't. Okay, we have an example with a function is continuous, but it's not differentiable. So in this regard, in order to prove a function is differentiable or not differentiable, right, with not differentiability, besides these tools, right, we also have an additional tool. That additional tool actually is the definition of derivative of a function at A. A lot of us may try to avoid using this tool because it looks complicated. You have to do calculation, but this one is the ultimate tool. You can work on limit, you can work on continuity, but in the case that limit exists and continuity also is true, you cannot draw any conclusion about whether the function is differentiable or not. So the ultimate one is the definition. So today I'm going to show you an example as to observe this limit, okay, to determine whether it is differentiable or not. So the first example is determine f of x, the derivative of f exists as 0, okay? Rather, we can say determine determine if f is differentiable as 0. As 0. Okay, so this is what we are trying to determine. And the function looks like this. Okay, so this is my earlier work. So I'm going to remove it because this is my second recording. The first recording, I wasn't happy with it, so I'm doing this one. All right, so you can try continuity. Okay, you can try limit, and they both are true. So those work would not be necessary. Because it doesn't tell you about differentiability as 0. So ultimately, we're going to determine whether this limit exists. So we're going to observe this limit for this particular function. Obviously, a is 0, so we got f of 0 plus h, 0 plus h. We can simplify it to be that, right? And then we're going to plug in, right, the limit. And then we're going to plug in to find f of h. We plug in h in the function. Since h is approaching 0, not 0, right? We need to be aware of the domain. So this is going to be h sine 1 over h. And minus 0, because f of 0 equals to 0. Okay, now we simplify this function, right? As this limit minus 0 can be omitted, and h can be reduced. So the limit is simplified to be that. Does this function has a limit as h approaching 0? So I put a graph here, which is sine of 1 over h graph. You can see the function oscillates between -1 and +1 intensely. So that's how it formed this little, area. Basically, is just this function sine 1 over h. It just oscillates up and down between -1 and +1. Limit does not exist. So this is the case we call it does not exist. And then by definition, it's straightforward. It's not differentiable. It's not differentiable, right? So we can be certain if we apply the definition, if the limit does not exist, then it is not differentiable at 0. So the conclusion is drawn. So let's look at another one. Okay. This is some preliminary work, I recorded with the previous lesson, which I ended up deleting, is that I tried to just, we analyze whether it's continuous. Okay, is this function continuous, right? And so we look at the limit, right? So we look at the limit of this function. And we use squeeze theorem, and we demonstrated that limit exists, and it is also that the function's value. So it is continuous. So f is continuous, right? But this piece of proof, right, I put it on the scratch paper. It's totally useless. It's totally useless to demonstrate it is differentiable. So you may think of that. This is what I meant, is that you may think of that. I'm going to use not continuous to show it is not differentiable. Sometimes it works, sometimes it doesn't. In this case, it does not. And in that case, do I need to show this part of the work to the reader? The answer is absolutely not. Not necessary. It's not necessary. Even though you did the work, but this work is not useful for you to prove it's not differentiable as zero, so then you don't need to use it. Okay, you don't need to turn in every piece of work you've done and let the teacher to pick and choose. If you let the teacher to pick and choose, and that shows that you may not be quite clear about concepts. Okay, you may not gain points, instead you might lose points. Anyways, let's look at the second example. Okay, the second example, I'm going to just remove the whole thing. Okay, I'm just going to prove it all over. Okay, so I'm going to remove that. So this is a different function. We still try to decide whether f is differentiable at 0. And of course, you can still try continuity, and I show you it is continuous, but that part of work is useless because continuity does not guarantee differentiability. So we're going to go straight to the block. Okay, we're going to go straight to the definition. So we're going to go to the definition, limit as h approaching 0, right? Definition of f to determine differentiability, we're just going to 0 plus h, subtracting f of 0 divided by h, right? So this is the definition of differential, the form of definition and the limit to observe. And if this limit exists, then it is differentiable as 0. If this limit does not exist, and then it is not differentiable. Once again, we're going to proceed. 0 plus h is h, right? And we're going to plug in. And f of h, we're going to replace x by h, right? So we're going to use this form of the function to replace f of h. And of course, x will be replaced by h. Okay, substitution. That's to get f of h. So this is f of h, and that's f of h. 0, f of 0 is 0. And subtracting 0, you can just remove it. And we have h squared here, we have h here. So we can reduce it to the next step. We're getting h, and this h is reduced. And so in the end, well, near the end, we get this piece. Does this have a limit? Okay, so in order to demonstrate this one has a limit or not, okay, we are going to try squeeze theorem. So I'm going to take this function of our interest, and I'm going to take absolute value. And because sine 1 over h, right, sine 1 over h in absolute value is less than equal to, right? So I'm going to put that statement in place, right? So it's well known that sine of 1 over this piece is less than or equal to 1. So when I take absolute value of h times sine 1 over h, that's going to be absolute value of h multiply the absolute value of sine of 1 over h. And because this piece is less than equals to 1, so this is going to be less than equals to the absolute value of h. So we got, okay, I'm rewriting it, and we got something like this. And from here, okay, if we recall that there's a model in algebra, right? we have absolute value of something, right? Less than equal to a number, say 3, right? And this is equivalent to that x is between -3 and a +3, right? So this is what we learn in algebra. So in our case, the capital X is this piece. So the absolute value of capital X, R3 is the absolute value of H. Absolute value of H is always a positive quantity, right? So our next step is that we are getting this absolute value. This absolute value, this is going to be, I just thought of it, I thought of one proof, and I thought maybe we can do it in another proof, right? So as a matter of fact, I can make it easier. Okay, we don't need to use this. Okay, how about this? We finished my first proof, and then we're going to show you the second proof, right? So this piece is going to be between negative of absolute value of H and smaller than or equals to absolute value of H. Okay, so this is the proof I thought of. Okay, I will show you another proof, which is even simpler. All right, so H times sine 1 over H, the limit of our interest, this function, is squeezed in between. Okay, so next we have reason to observe the limit above and below. So the limit of absolute value of H as H approaching 0, obviously is 0, we all know that. And the other limit, of course, is also 0 if I remove the negative sign. It's also 0. So those is very, very well known. So by squeeze theorem, I hope I did, I deleted that. So by squeeze theorem, okay, and this function that's squeezing between that limit is 0. And this limit is 0, but this limit is equal to that limit, right? So we're going to make that connection, i.e., that limit, not only it exists, it also is equal to 0. So this is the direct application of differential derivative, and the limit exists, right? So definition applies, then we can say thus, f is differentiable as 0. F is differentiable as 0. So this is done, proved. On the, I promise you, I'm going to show you a simpler proof, right? The simpler proof actually starts from here. Okay, so a simpler proof. Okay, a simpler proof starts from there. Also, okay, because this piece is taken absolute value, so naturally it is greater than equals to 0. This is always true, right? No matter what is the H. So this way, that function is squeezed in between. So next, we just need to bring this with us, right? Since this is approaching a limit equals 0, the limit of 0 is 0, right? And therefore, we have by squeeze theorem, theorem, by squeeze theorem, this limit on the absolute value is 0. If the absolute value of something is 0 as h approaching 0, and of course the quantity inside is going to be, it's going to have a limit of 0. Okay. Therefore, that limit without the absolute value is also 0. So this is another simpler way of proving, this limit is 0. And so we have proved that f is differentiable at 0 for this function. So we have 2 examples today, right? These 2 examples demonstrated that using definition of derivative is still the ultimate tool to prove differentiability or not. But we also have those, sidekick technique we can use. Okay. If the limit does not exist, then there's no differentiability. If it's not continuous, is not a differentiable. So it seems that using these relationship is also helpful to determine, in those different circumstances. And there are many, many examples we can address, but I try to make this short. If you have any questions, please don't hesitate to reach out to me. Thank you for watching.